Hi, I'm Nguyen, and this is my AP Calculus extra credit assignment. My function is going to be Rx equals x cubed minus 6x squared minus x plus 30 over x cubed minus 7x squared plus 12x. Here's my sketch of Rx. So Rx is made up of two functions, f and g, f over g, and then fx is the function on the top, and then g is the function on the bottom. Fx have roots at x equals 3, 5, and negative 2, while gx have roots at x equals 0, 3, and 4. The roots of rx are at x equals 5 and negative 2, and the vertical asymptotes of rx are at x equals 0 and 4. Rx has one horizontal asymptote at y equals 1, and then Rx has one removable discontinuity at x equals 3. Here's my detailed graph of Rx, where green is Rx, red is the vertical asymptotes, and then orange is the horizontal asymptote, and the whole here is the removable discontinuity. So the limit as x approaches 0 from the left is negative infinity, and then the limit as x approaches 0 from the right is positive infinity. And then for x equals 4, the limit as x approaches 4 from the left is positive infinity, while the limit as x approaches 4 from the right is negative infinity. And then the limit at the removable discontinuity is 10 over 3, and I got that by factoring out x minus 3 on the bottom and the top, and then just putting in 3 to get the limit. So the limit as x approaches negative infinity is 1, and the limit as x approaches positive infinity is also 1 because of the horizontal asymptote at y equals 1. So overall, Rx is continuous on negative infinity to 0, united with 0 to 3, united with 3 to 4, and then united with 4 to infinity. So here's my first derivative. It is negative x squared plus 20x minus 40 over open parentheses x squared minus 4x close parentheses to the power of 2, and I got it using quotient rule. And then here's my second derivative. It is 2x cubed minus 60x squared plus 240x minus 320 over open parentheses x squared minus 4x close parentheses to the power of 3, and I got that by using chain rule at the bottom and then using quotient rule for the rest of it. So here's my analysis of the first derivative. So we have intercepts at x equals 5 and negative 2, critical points at x equals 0, 2.254, 4, and 17.746. There's a local minimum at x equals 2.254, and then a local maximum at x equals 17.746. Rx is increasing on this interval, and then it is decreasing on this interval. Here's my analysis of the second derivative. So we have the critical points at x equals 0, 4, and 25.548. There's one point of inflection at x equals 25.548 where Rx goes from concave down to concave up. So Rx is concave up on this interval and then concave down on this interval. My MVT problem for Rx is going to be on the interval 6 to 8, and for C I got about 6.815, and then here's my drawing for MVT. For IVT, I chose the interval 4.5 to 6, and then, well, Rx is continuous on this interval, so that means that, and then 4.5, R of 4.5 is a negative number, while R of 6 is a positive number, so that means 0 is definitely in between these two numbers. So that guarantees the existence of my root of x equals 5. So for EVT of Rx, I chose the interval 7 to 10, and since none of the critical points of Rx are inside 7 to 10, the endpoints are going to be the absolute extrema. So after I calculated what R7, R10 equals to, I can conclude that Rx has an absolute minimum at x equals 7 and then an absolute maximum at x equals 10. So for my tangent line, I put in 1 into the original Rx to get the 0.14. And then for the slope, I actually put in 1 for x into the first derivative to get negative 7/3. And then for the normal line, I just got the negative reciprocal of negative 7/3, which is 3/7. And that's how I got the normal line. Here's my work. And here's my sketch of the normal and tangent lines.